Okay, then please allow me to start this session and introducing first Gianluigi Seriani. So as I mentioned with all the speakers, you are able to find the bio of all of our speakers in the Indico page. So I will just briefly mention that Gianluigi is coming from Consorzio RFX in Padova. So he's responsible there for the scientific exploitation at the ITER neutral beam test facility, which is precisely located at Consorzio RFX in Padova. And then, yeah, please, Gianluigi, let us know what is it that you guys are doing there at Consorzio RFX. Please, the floor is yours.
Dario, thank you very much for this introduction. Just let me share with you my presentation. At Consorzio RFX, actually, we carry out several activities, and it's a pleasure for me to describe them to you in this context. Actually, fusion research in Padova dates back from many years, and the latest experiment, which is dedicated to investigating the plasma in fusion relevant conditions, is a reverse field pinch machine. So this is the magnetic configuration, which is adopted in the RFX and its followers, let's say RFX mod and mod 2. The mod 2 is actually presently under finalization because we have rebuilt the vacuum vessel in order to make it larger. So here is just a few data regarding the target parameters and what we obtained. So essentially we met all the parameters. As you probably know, this is a sort of side line with respect to the tokamak in order to reach at the end the fusion reactor. We are much, let's say, about 20-25 years later than the tokamak. This line of activity started later on. Anyway, this is just one of the activities that we carry out at Consorzio RFX. You can see it, the RFP, reverse field pinch physics. But we also have a collaboration with through Europe with the Japanese colleagues for the new tokamak, which is under finalization. And we cooperate with several other medium-sized tokamaks in Europe, and also with JET, of course. Apart from some other small activities in plasmas, applicative plasmas, I will come back to some things about some information about the education. The other major activity that we carry out is the one that actually I'm involved in, so it will be the core of this presentation. That is the finalization of the design, the optimization of the experimentation of the neutral beam injector for ITER. ITER will be provided with two of these injectors, which require, in order for the particles to access the core of the plasma, 1 megavolt energy, which neutralize. Of course, these particles have to be neutralized. So we will see that this calls for the using not positive ions, positive hydrogen ions, but negative hydrogen ions, and actually the parameters required of the beam, the current density, the divergence, that is the tendency of the beam to get larger and larger as it goes from the accelerator to the plasma, and also the uniformity across the beam, which is more or less more than 1.5 meters tall and 60 centimeters wide, have never been attained simultaneously, and particularly for 1 hour. So much so that ITER decided to set up an independent laboratory, which is in Padova, in which is the core of my activity. 2 experiments are located in Padova. One is the entire one-to-one copy of the injector, and which we call Mythica, and the other one is a full-scale source of the injector, in order to decouple the problems of the source from the problems of the of the accelerator. So this is the facility. You can see there is the, let's say, the small experiment spider and the large experiment, which is a real one-to-one copy of the injector for ITER. You can also see that the power supplies for the injector. This is the injector inside its bunker. The power supplies for the injector are even much larger than the injector itself. So I was saying that we are using negative ions, and this is the key. The reason is that when you need a large energy above, let's say, 150 kilovolts, in reality, you cannot use positive ions because as they have to be neutralized by passing through a gas cell, you have to deal with the efficiency, and the efficiency really drops down at 1 MeV. Essentially, it's impossible to neutralize the positive ions. Whereas the opposite is true for negative ions, which after initial decay will retain the neutralization efficiency effectively constant up to 1 MeV. So the problem of neutralizing the particles turns into the problem of generating the negative ions with this final goal, final current, which is quite huge, in order to deliver at the end of the day 16.5 megawatt per generator to ITER. So as I said, we have two experiments. The one is SPIDER, which is the source with a 100 kilovolt accelerator. And here you can see most of the parameters. I draw your attention on the very large current density for a negative ion source. So for positive ions, you can have 10 times as much. Okay, so the source itself has got some technical problems. I will first go through the technical problems in order to show you that we need to work together. I mean, physicists and engineers need to work together because the problems we have to face are interlinked. It is a very large source which fully sits in vacuum. Actually, it's not vacuum, it's a low pressure. So it's the worst condition in order to hold 1 megavolt voltage. We have a plasma which is generated by 8 radio frequency drivers, which again adds to the possibility of interference between them, and so reducing the power which is really coupled to the plasma. Okay, so this just to say some of the problems, but one of the biggest problem is the voltage holding. Here you can see a cut view of the entire injector. This is the source plus the accelerator. The accelerator is 5 stages, 200 kilovolt each for a total of 1 megavolt. And then there is the neutralization stage. Neutralization is anyway efficient only up to 60% in proper conditions. So some residual ions remain, which have to be dumped because anyways they would not enter the ITER plasma. And then of course here in Padua, we do not have the ITER plasma, so we dump the beam onto a calorimeter, which has to sustain more than 16 megawatt for 1 hour. Okay, so this is the system. As I said, the power supplies are much larger than the real injector, and what we have been doing now is to operate the large voltage and large current power supplies and check the voltage holding. This is this is the result. This is the example one test at 1.2 megavolt for 1 hour, which was successfully passed. And then at the moment, we are waiting for some of the mechanical components to arrive. On the other hand, we are repeating these voltage holding tests by adding them as they come to our institute. So these are some other techniques which are used in order to help voltage holding by installing intermediate layers at intermediate voltages around the ion source. The ion source, which I repeat, is in vacuum at low pressure, actually, at 1 megavolt from the vessel, from the vacuum vessel. Okay, concerning SPIDER, SPIDER has the one-to-one copy of the source with 100 kilovolt acceleration has entered into operation in 2018. We operated it for 3.5 years, and now we are in a major shutdown in order to make it better. We'll come back to this later. But first, now let me go to the physics. How does the acceleration takes place? Okay, so we generate a plasma, which is inside a sort of plasma box. So one of the sites is provided with several apertures. In our case, more than 1,000 apertures, through which the plasma can bulge unless you apply voltage with respect to the first grid of the acceleration, what we call the extraction grid, because it is the voltage which is applied between the plasma grid, the grid which faces the plasma, and the extraction grid which takes the negative particles out, like D minus or H minus. Unfortunately, when I say negative ions, I really mean negative ions, including electrons, which of course are not the ones that we want to accelerate. So much so that we install magnets, permanent magnets inside the extraction grid in order to dump the electrons onto the same grid. But this deflects the negative ions so slightly, but you have to think that from the accelerator to the plasma, you have 25 meters, and you have to go through several beamline components and through the duct which connects the injector to the ITER plasma, which means that even if the requirement on the direction of the beam is not larger, you cannot afford more than 2 millirad error, which means 2 millimeters every meter. So otherwise you dump a lot of power in intermediate structures which are not designed for that. So we have to take care of that. Okay, but let's go one step backwards. We create negative ions. We create negative ions in the plasma, but we want them to be extracted. So to survive up to the region where the extraction occurs. In order to create the plasma, of course, you need to be in terms of electron temperature on the right-hand side of this figure, so high electron temperature, but this destroys the negative ions whose binding energy, I mean the additional electron, the second electron for hydrogen or deuterium, is very loosely bound, just 0.75 eV, so it's very, very easy to remove it. So much so that you need a region, you need electron cooling, because when the electrons reach this region through where they are extracted from the plasma, the negative ions should be in the presence of very low temperature electrons. And this is accomplished by means of a magnetic field, which is vertical in this drawing, which separates the region where the plasma is radio frequency generated from the region where the negative ions are extracted. So we exploit the low temperature part in the vicinity of the extraction grid. This magnetic filter, as we call it, is actually working properly, as you can see from experimental measurements that we carried out in SPIDER. Okay, we have 8 drivers, as I said. They are not, unfortunately, the same. So in the plasma, we didn't find this, measuring the plasma properties, we didn't find that they are uniform from driver to driver. And this is just the first hint that we can have a major problem in terms of beam uniformity. I will come back to this later. Partially, this was due on a on an interference between the filter field that I mentioned and the magnetic field, which is made of cusp magnets all around the plasma box. We are curing that during this shutdown. Okay, we need to create a lot of negative ions. Unfortunately, even though negative ions can be generated inside the plasma volume, this is not a very efficient method. There is a much better method, which was essentially devised by the Soviet colleagues in the 70s, which essentially counts in depositing a layer of alkali metal, specifically cesium seems to be effective, onto the plasma grid itself. So the positive ions and the neutral atoms, which impinge onto the plasma grid, bounce off with up to 30% probability as negative ions. And they're already there where the electron temperature is low and where they're pretty close to the extraction. So it is the most favorable position. So we have to deposit this cesium layer, and this you can see what it really looks like after opening the source during the present shutdown. So it's pretty dirty just because cesium got oxide. Okay, so we another issue that I mentioned earlier is that we extract from the plasma negative particles, so electrons included. We may bias the plasma grid with respect to the plasma box surfaces, and this already reduces the amount of co-extracted electrons. We can use another plate which is just before the plasma grid, which also cools down the electrons. But the most important thing is, as I mentioned at the beginning, is magnets which are embedded into the extraction grid, the first grid of the accelerator. Unfortunately, as I said, we have to recover the proper direction of also of the negative ions, which are slightly bent. As I said, they have to go 25 meters before they reach the plasma, and this is part of the experimentation that we are carrying out to check whether the correction of the deflection is proper. Okay, it is a plasma. It is a large plasma, 1.5 meters tall. In the magnetic field, we have plasma density gradients. We have gradients of magnetic field even. So we have electric fields. So at the end of the day, we have a lot of plasma drifts inside. So it's a live thing. Our plasma is a live thing. As always, the plasma is sort of self-organizing structure, which means that we end up with, unfortunately, local non-uniformities. And this is what we do not want, as I mentioned earlier. Some of them just comes out of the fact that we are overlapping the result of several radio frequency drivers. And this is an example of the real profile. You see that in correspondence to each driver, we have a sort of hill. So the current density that we will extract, which will constitute the beam, is not uniform, unfortunately, across the surface. So this is another issue we have to face.
Yeah, Luigi, I have to be the moderator and speed you up a little bit. So
okay, sorry, yes. Okay, it was just last one. From the physics point of view, is that if we have a large variation of the density, that this turns into a variation of the size of the beam, or the divergence, which are somehow balancing, which means that with a long accelerator, we might hit directly the accelerator grids. Okay, what we are doing now is to work on the plasma. This is just present activity in order to improve the plasma confinement. I will skip the results, just a few words about what we can do in terms of education. We have normally several students which work with us, help us, both at the bachelor level and master thesis, mostly from Padua University, but not only from there. And we have a PhD course on plasma physics and engineering, which is based at Consorzio RFX, because one of our partners is Padua University. Thank you very much for your attention. Sorry for being late.
Thank you very much, Gianluigi. Sorry to speed you up. I know you have impressive facilities there, so there is a lot of topics to discuss. So yeah, I'll thank you so much. I'll move next to Daan van Vugt. Then Daan is he was a master student here at TUE in fusion, and now he's the head of a company, Ignition Computing. So he's, correct me if I'm wrong, you are the CEO of the company. And then Ignition Computing, last time we spoke, you had 5 contracts already with ITER and ITER-related developments. So, and yeah, please go ahead and please tell us what Ignition Computing is doing. And
Yeah, thanks, Dario. Yeah, so I will give a little introduction in, say, my career trajectory, the founding of Ignition Computing, and then I have some remarks on integrated modeling, what could be nicer there, and what we are doing to make things nicer. So let me share this presentation here. All visible for everyone?
Yes.
All right. Yeah, so let's start with me. I have done a Bachelor of Science and a Master of Science in Applied Physics at the University of Technology in Eindhoven. And besides, I have a lot of freelance software development experience. And then I did a PhD in fusion in the fusion group in Eindhoven in a project together with ITER, developing extension to the MHD code JOREC to allow for particle and cell extensions in Monte Carlo. This was mostly focused on tungsten transport and sputtering, and now it's been extended to even do turbulence calculations. Near the end of the PhD, I realized I enjoyed writing all of this code a lot more than I enjoyed writing papers, and so I figured how to get into a career path where this is interesting. We started a few side businesses after service, track lead, and join. And besides that, the fusion hook was still in me. So I was starting discussions with Differ and with ITER on doing some work for them. And out of this came ignition computing. And so we are running since 2020. The idea is to build software powering science. We're doing consulting for high tech and scientific software. We're 7 right now and looking for more. And we have a strong track record with machine learning projects, software development, numerical methods, building high performance computing stuff, doing visualization, performance optimization for a variety of clients, the largest of which is ITER. And most of that is for the science division in ITER, where we are helping with their integrated modeling toolings. And so I want to talk about, let's say, the exciting developments in Fusion right now, where we are close to getting a new set of experiments on ITER, hopefully 2025 first plasma. I guess you've heard a lot more about this morning. And also Spark is very interesting. And all of these advances are really not so useful without modeling. We need a lot of modeling to interpret the results that we will get from this, to constrain the measurements that we are getting, to validate our understanding of the physics, to predict the profiles that we will get, to make sure that everything is safe, to predict the performance of hypothetical future reactors so that we know how they will perform and what size we need to build, and to optimize the designs of the reactors that we are building. And finally, if we want to control how the plasma will behave inside, we need to have our modeling to design these controllers. You need a kind of digital twin-like system. And for these cases, you need very, very fast models. And this is a bit of a problem because the present day models that we have, at least the high fidelity models, are far too expensive for our typical experiment prediction. And there are a lot of different reduced models available, which have limited application, limited domain, limited resolution, or reduce the physics that they are including. And this is very important, but we need a leap in capabilities to combine these models to get a fuller digital twin-like setup, to go to reactor scale and to really fully predict how our machines will behave. This is difficult because plasma multiphysics modeling is hard. I mean, you are master students in Fusion, so you know some of this. And there's a huge range of length and time scales, and there's many different disciplines, specialisms coming together to combine in our understanding of a fusion device. So I have a rough map of the length and time scales which are relevant in our devices, and this can be fleshed out, and there are many, many more disciplines that can be filled in here, all of which overlap in some parts and don't in others. So together with the limited experimental data that we have on this, it's quite hard to make good integrated models of machines. There are some cool things which are happening. Here is a nice example from the Jorek code that I worked on. Not this example specifically, but some of the tools that went into this. So you see here an ELM simulation in MAST and the comparison of the resulting data with a fast camera image. And this is the kind of, let's say, validation of your code that is really important to get to, even if this is only a qualitative validation, to get trust in our modeling. And so if we think a little bit about what goes into making just an image like this, you have your reference, let's say your fast camera images on the top left, which come from an experimental database. And you need to have a synthetic camera diagnostic on your outputs to make comparison images. The input to that is a calculation of the radiation at each point, which depends on the atomic coefficients, which have been calculated with a different code or are available in the ADAS databases. And the other input is your time-dependent MHD equations to solve for your ELMs, which have an input as the transport coefficients and a lot of physics coefficients and settings in Jorek, and also the equilibrium. And this one you tweak based on the wall shape, based on the field, and based on your target equilibrium that you are trying to compare against. These depend on the coil currents again. And so there's a whole tree of dependencies and of tools that you need to work together with to make even a result with a simple code, or with a single code, let's say. And especially if you are going to be including multiple codes that do separate parts of the physics, you get very complicated co-simulation systems. And this is an example from 2018, where there are several codes which perform separate simulation tasks combined into an integrated modeling. You see, for instance, your calculation of turbulent transport coefficients and neoclassical transport coefficients, which influence your heat, particle, momentum fluxes, which determine the profiles, temperature, density, etc. And those again influence your bootstrap current, your flux evolution, and again your transport coefficients. So to do a kind of consistent simulation of this, you need to include these, and you need to do a full co-simulation. And never mind all of the extra external influences that you want to support and that you want to be able to simulate, your controllers, your sources, your pumping, all of this together. And to get a good understanding of what is going on, this needs to be integrated. And I mean, in 2018, this was new and impressive enough to be a research paper, and now still it's a difficult project to build an integrated code like this. And so this is one of the things that we want to make easier, because it's really important that it's accessible and it's possible for scientists to develop this kind of integrated modeling simulations. And so I want to take you into a little dream of how things could be, and then think for yourself how much of this is already present. We'd like to have our data be open, accessible, fair, so findable, accessible, interoperable, and I forgot the R. But the code should be publicly available. The documentation for them should be good. The set of instructions trustworthy. And then the data structures that these codes output or input, they need to be interoperable so that you can chain your codes together. You want to have tracking of the dependencies and of the provenance of your input data, of the who has messed with the experimental data. You want to have co-simulation where you really have to run codes at the same time, iterating to get a solution together. You want to have the option to integrate controllers into your physics models and to update your controllers with physics models to develop them. So both ways. You need sensitivity analysis, something like differentiable computing or UQ methods, so you know how your outputs depend on your inputs. You need fast local surrogate models to develop controllers to do real-time control. And in general, you want these simulations to be fast enough so that you're not waiting for 6 months for a result. So we'd like to make this one a reality, all of these. And specifically, there are 5 points that we are working on right now, which we think are helping. So the second one, the publicly available codes, there we have a strong open source heart in this, and we are pushing to make this open, and we are hoping to push ITER to open up the documentation on some of the codes that we have developed. For the interoperable data structures, there is work on IMAS at ITER that we are improving the APIs for. On co-simulation, we have a lot of work on a new method, a new paradigm for co-simulation. And we are trying to apply that to a controller integration in physics models also. And finally, we have an internal project to increase the performance of simulations with machine learning, a data-driven approach to reduce the amount of work that needs to be done at each time step. And so specifically, since this is the ITER-related companies, I'd like to highlight 3 out of these 4 projects that we are doing for ITER. One is on high-level APIs for working with fusion data, one on these infrastructure for co-simulation, and finally one on data-driven simulation acceleration. So for the high-level APIs, maybe you have heard of IMAS. It's a system of standard data structures that has been developed over the last, well, at least 10 years, and where there are APIs in different languages that can write and read the same data. So they act a bit as compatible data types between codes, except that you have to write them to a backend. And so for this, the tooling is available, but in my opinion, it could be better. And we got some contracts to improve the current APIs and to build a new one in Python, which is flexible and not code generated, but on demand generated. And this one can do really cool stuff enabled by the dynamic nature of Python, such as on-the-fly data conversion between different versions of these data structures. We have optimized the performance quite a bit. There's a much nicer development experience if you are using this. We are hoping to get to a pip install IMSPy pretty soon, and there are a bunch of new features coming up. On code simulation infrastructure, I can give you a little preview of what we are working on. There is a toolkit called Muscle3, where you have a different approach to running your simulations. Instead of having, let's say, a driver Python script or something similar, which starts each code step by step and has all of the setup overhead each time, this new approach starts all of the code simultaneously and relies on messaging between codes. This means you can have several types of communication, like the three shown on the right: dispatch, interact, and call and release, and combine all of these, describe your coupling with a declarative YAML file, which indicates or which contains all of the ingredients to start your simulation. And because the state is kept within each time step, it's much faster. You can skip the disk for your communication because we send messages between each other. This can even be a shared memory system, and you'll get very easy cross-language support. So we have been working on implementing the IMAS data structures in this. We have a really cool project on distributed checkpointing, where it's a way to mathematically prove that we can checkpoint and to implement this, even if there are multiple actors running at the same time, at different time steps, etc. So that in your integrated coupled simulation, you can restart after a while if all of the individual codes support this. And we are looking at making a proof of concept for the integration of one of the control systems from ITER with the high fidelity plasma simulator. Remind again this example from before, where each of these steps were before being done as method calls in a custom code, but actually with this new approach, they could be actors which have a specific job and which receive messages on their input ports and produce messages on their output ports. And so each of these could run at the they could run in a cloud allocation, they could run locally, and you can rearrange the simulation structure more or less as is allowed by the kind of messages that these actors can receive. So this is a very flexible way of doing things, and we think is really really worthwhile and has a lot of potential. Finally, a little bit about this data-driven simulation acceleration. We have an internal project which is in closed beta on accelerating matrix solutions by using data on the previous matrices that were solved. And one example is with a plasma simulation code from a company called Plasma Matters in Eindhoven, where we demonstrate a better predictor for the next time step and a dynamic solver choice algorithm, which together gave us a factor of 6 speed up in the solve phase of their code. So this is a really promising result that we hope to bring to Fusion codes in the near future. So this is a bit of an overview of the things that we are doing. And if this is interesting to you, we are looking for internship students, and we have an open position now. And I'll be in the Gather Town later. So if you have any questions, or ask them now, ask them later, or check our website. Thanks.
Thank you very much, Dan. Yes, actually, it's a good that you mentioned the questions because we have some more questions for you in the chat session. And since we are running out of time, a bit late, then we will propose that you please answer directly these questions in the chat box, and then we will move with our next presentation. and also for Gianluigi if there is any question. So please, all the Q&A is moved now to the to the chat box, and then
Okay.
I will give. Thank you, Dan. So I will give the floor to Blanca Biel. So Blanca Biel is an associate professor in the University of Granada in Spain, but she's also the co-director of a joint school between the University of Granada and the IFMIF-DONES project, which it has been mentioned already before, the importance of the IFMIF-DONES project within the fusion roadmap. So please, Blanca, the floor is yours, and tell us, welcome, and tell us what is going on there in Granada.
Thank you very much, Dario. I guess you can hear me. I'm going to try to share my screen. So please, if you could confirm that you are seeing it.
Not the full screen.
Okay. Now it goes, because I'm in principle, yeah, I should be in presentation mode.
Maybe you're in the other screen. Probably you have two screens.
Okay, let me see. What do you mean? Two screens?
Because we not see the presentation mode yet.
Yes, I know.
Okay.
I know, but yeah, I don't know why, because I'm really trying to switch here to the presentation mode, but
presentation mode is down. It's, yeah.
Sorry about this. No.
No, you have to share screen again.
Yes. Okay. Yeah, I know that when sometimes we are having this type of things, problems with the.
Okay, we're seeing other town.
Sorry. I thought that. Yeah, so you should be seeing the presentation now, but now let's see whether I can manage to put it in presentation mode. Yes, sorry about that. Okay, so I guess now you can see it, right?
Thank you. Perfect.
Sorry very much. Really sorry about this. So thank you, Dario, and all the other organizers for inviting me to be here today. So So Dario mentioned, I'm here to tell you a little bit about the IFMIF-DONES project, but also especially about the initiative that we are creating within the framework of this consortium between the DONES project at the University of Granada. So since I'm not really part of the DONES project, I'm going to give you, nevertheless, a quick overview. So just to try to show you the challenges and the opportunities that the DONES project can mean for all of you. And then I will tell you a little bit about this exciting school. So I guess all of you are familiar with this roadmap for the fusion energy. So the DONES project is actually very much related to DEMO. And why is that? So, you all know about ITER. We've had several talks on ITER now, but one of the things that you might not know is that there is a big difference between the technology in ITER and the technology in DEMO. And one of the main differences is that the radiation dose in DEMO is more than 2 orders of magnitude higher than in ITER. What does this imply? So the thing is that when we are going to build DEMO, we have to be sure that we have the right materials to actually build that facility. Right? So that's the main goal behind the DONES project. So the idea with DONES is try to get the effects of a fusion reactor without actually having to build that fusion reactor. So it's going to be some kind of simulation, if you will. So how can we get this effect? So what we actually need is to have neutrons with similar effects to those that are going to be created in the DEMO facility. So in order to get that, what we need is actually an accelerator, a powerful neutron source, which will be built just to be able to qualify the quality or the ability of these materials to to go on these extreme and critical conditions. So actually, the DONES project was identified. I mean, it's been, I think, more than 20 years ago that the people started thinking about how to achieve this way of actually testing this material. So the DONES project was identified as a high priority initiative in the European roadmap long time ago. So the mission of the DONES program is to develop a database on the effect of these fusion-like neutrons on the materials. There are many materials that are being studied right now, but we really need to test them before. So the objectives of this DONES program is to provide the neutron source, to check the material, to do the radiation test data of these materials, generate this database of materials so that we can choose which materials can be used in the different parts of the reactor, and also try to think of other possible applications that we could use DONES for. So we are going to build the accelerators. So what else can we do besides testing these materials? So of course, as you can imagine, this is a project that has many challenges, and I'm just going to show you some of them so that you see that regardless of what your area of expertise is, or even if you're working on a particular project, what is maybe you have another interest, another things that you would like, another ideas that you would like to develop. So I'm just going to give you a very quick and brief overview of the challenges that are already open questions here for DONES. So for instance, we have to develop more technologies for the accelerator systems, the radio frequency, the microwave power systems, the cooling systems, the power converters. We have to develop more technologies for the lithium systems. We have to develop more technologies for the test systems, the ultra vacuum, the remote handling. I think we've been hearing a lot in this event, so that's really important thing. Technologies for the building, for the plant systems, for the management, so from safety and security to logistic, artificial intelligence for plant supervision, for predictive maintenance. And as I was mentioning before, we are already thinking of possible complementary experiments that could be done at the same time that we are testing the material. So we could have, for instance, application of medical interest for radiopharmaceuticals, or boron neutron capture therapy that I think you might have heard about. It is something that our department is very active in the University of Granada. Basic physics studies, more studies on nuclear physics, on radioactivity, and of course, other potential industrial application of neutrons. So as you see, there are lots of things that I hope can give you ideas about what else to explore here, and I hope you feel that you might want to contribute to this project. So when or where is this DONES project going to be built? So it's going to be built in Escúzar, which is a small village in Granada. So Granada, as you probably know, is a city in Spain, in the south of Spain, in Andalusia. So the reason why DONES project is going to be built here is because there is a consortium between the DONES, the IFMIF-DONES, and the University of Granada, so that the regional government and the university, they are contributing strongly to the funding of this project. So there are already lots of interactions between the university and researchers from the DONES project. There are several research lines co-advising PhD students. All of them focus on different investigations related to the DONES project. So Dario asked me to try to tell you a little bit where are we in this roadmap. So actually, I can tell you that we have, I think, right now more than the 50% of the funding approved. And actually, last week, the king and queen of Spain, together with the Ministry of Science, they went to Croatia to start, which is going to be the first of many different international agreements with other countries, so that there is a strong consortium to support the whole funding of the DONES project. So actually, this picture here, I think that was taken last week in Croatia. These two pictures here, some of you might know some of the people involved here in the project. These two pictures were taken, I think, yesterday in these facilities in the schools that are being built. So this is the first step, which is the office building that is, as you can see, already under construction. But now the thing is, how are we going to get there, right? So because we have the building, but that's, as you know, that's not by all means the most important. So something that we need, and it has been made very clear from the beginning of this event, is that we need people. So as was said in the inaugural section, in order to solve problems, we need the right people to do it. And that's why I think it's great that there are initiatives like FuseNet to provide education and to provide tools for all of you to increase your knowledge and your expertise in fusion technologies. So within this framework, we thought it would be actually very good to try to contribute to this knowledge. So we've decided to start something new, which is a school on science and technology, and the name is Excited. And this is a school on actually not only fusion technologies, but any big science technology, although of course, since it's funded by the DONES project, is going to be also very, very much focused on fusion. And this is organized jointly by the University of Granada and the Consortium IFMIF-DONES Spain. So what will the topics of this school be? So it will be focused on, as I said, fusion devices and of course neutron sources, acceleration technologies, so all these technologies related to the DONES project, but also we will offer more general courses. So we will offer courses of course, material science, right? Nuclear physics, medical applications, environmental challenges in big science. So I don't know if you've heard about that, but of course, I mean, we know that we are in a planet that is being environmentally challenged right now, but actually typically big science facilities weren't very aware of that, or we weren't really paying the attention we should have until now. But now this thing is radically changing. So the idea is that we are going to try to build a big science facility which are sustainable from the very beginning of the design. So I think it's going to be a very important line in the future. So the goals of this school is to offer training and education on all potential technologies that can be needed for big science, so we can provide a highly qualified professionals like you all. And very, very importantly, we would like the school also to be a medium point between academia and industry. So the idea is that we will have also our industrial partners contributing to the school from the industry point of view, so that you have not only the point of view of academics, if you want, or even of people who have been working directly on the big science facilities, but also people coming from industry. So the idea is that we will offer several courses for each edition of the school. So for this first edition, which is going to be held actually in the spring of 2023, so we are planning to have two different courses. So the first course is going to be, the director is going to be Moises Weber, whom you might know. And he's one of the pilots, I would say, of this DONES project. And he's going to tell us about what is DONES, but in depth. So why and how IFMIF-DONES was thought, which are the main technologies and systems that are going to be used in the IFMIF-DONES facility, which lessons we learned from other accelerators, from other nuclear facilities. Actually, I think this is one of the biggest strengths of the school, that all of the people involved, they've been working on fusion from since many, many years. And I think that's very important, that you are going to learn directly firsthand from them. He's going to suggest, or we are going to discuss about alternative applications of the neutron source. And again, very importantly, the collaboration with industry, how to get there, how was the road that was traveled from his experience, and he will tell us some success stories. And maybe from these stories, you can also learn in the future. You might want to start your own company, or yeah, I guess all this can very well be an inspiration for you. The second course is going to be, the director is going to be Eberhard Giegele, and is going to be focused on materials, of course. And yeah, so it will be about the materials that we are going to need to build DIMO, for instance, but other facilities. What is the effect of the radiation of materials, something that is going to be critical. How can we model these effects of radiation, the degradation of the materials, the fusions, neutronics. So, I mean, anything you can think about when you are trying to design a new material or to test some of them, what you would need to know about it. Of course, these are the direct, I mean, Moises and Eberhard are going to be the directors, but they are not going to teach themselves all of the lectures. So I can tell you already that we are having some big names here coming from this edition. Yeah, so I encourage you to subscribe to our newsletter so that we can tell you probably in the next few weeks who else is going to come here to teach. So I don't think I need to tell you the why. Yeah, we need to have professionals trained here. You are already working on fusion, but some people out there, they are not, and they might be interested. So this is open to everyone. I told you already, this school is going to be held in Granada. You may wonder why Granada. Well, there are different reasons. One is that it's a very beautiful city. We have the Alhambra, which is the Saraf Palace, which is very well known. We have beautiful mountains, and actually the first snow just came this past weekend. It's really beautiful already. But it's also a science-oriented city. We have the second oldest university in Spain. We have a very big science park, which is also very visited, and we have a very, very important also bio health park with lots of industries and facilities. So yeah, Granada is now not only a historical city, but also a science-oriented city. So the idea for the school is that, in principle, in this first edition, we would like to keep it small. So we would like to really have a school character. So in principle, we are thinking of only having 35 students. You are going to be accommodated in a very beautiful and old building of the university, very close to where the school venue is going to be. So this is the school venue, it's the School of Architecture, which is a beautiful building that has won also several prizes for the design. And it's actually, these two places are very, very close. We're already thinking about trying to interest you in science. I mean, take advantage of the beautiful city with some social program that allows you to, for instance, visit the Alhambra and have our gala dinner in another historic university building just in front of the Alhambra. But we are also thinking of trying to communicate or to connect with the big public there. So we are preparing also a strong outreach program so that some of these big people who are coming to teach you also will be able to speak to a more general public. So to try to make them understand the importance of nuclear energy or fusion energy, talking to them in general terms. So that's also a very important part of the school. So this next edition, as I said, is going to be in the next spring. So the idea is that it's going to have an annual periodicity. And as I said, you can go to that website, and registration is not open yet, but you can subscribe to the newsletter so that you are kept updated with the newest developments. So also I mentioned before, it is taught for people like you, master students, but also for people who are already have started already their PhD, and also people working in industry and who would like to learn more about fusion and big science application. Yeah, this is everything I wanted to say in this time that I have. So I really hope to see you next spring in Granada. And yeah, thank you again for your attention.
Thank you very much, Blanca, for this overview, especially with the nice, nice pictures of Granada. You have a question in the chat, so you will be so kind to answer it. That would be great, so we can move forward. And I would like to thank all the three speakers. Thank you for showing us the projects that you're working on. And I hope that we will be able to link you with the students present here, so the students have the opportunity to join your different projects, companies, and then all together we will move forward in developing Fusion further up. So thank you so much for being here.